All right, we talked about section 1.3. Well, you guys watched videos about section 1.3 while it's gone. And this description or this type of way of finding a limit is called either analytical or algebraic. So those are two interchangeable words that you need to remember. They mean the same thing. So there's three ways of finding limits. Graphically, there's no question about what that means. You guys get that. Numerically means with a table. And then either algebraic or analytic means the same thing, and it means using algebra. So we talk about the fact that there are some things that are just beautiful. So whatever happens when you have a constant, b is a constant here, it doesn't matter what this limit as x approaches, you get b. And the reason for that is because all you're really looking at is a horizontal line. Well, I mean, like, it's not very exciting, right? Things are not changing, so it's just going to be whatever that y value is for that horizontal line. When we have this equation, it's just x. That's a line that looks like this, like y equals x, right? When x is equal to something, y is equal to the exact same thing. So on this one, whatever we see the limit value approaching, that's what the x value is actually going to equal at that point, and correspondingly what the y value will equal. And then the last one down here has the very nice feature and everything we sort of hoped and wished would be true. And again, it kind of follows with number 2, that whatever the x value is, we simply evaluate x for that value of c. Okay, so kind of everything we would sort of hope to be true is happening for us. And then another set of things that, again, everything we hoped would be true is true. This is saying that if I have a constant and I have a limit that I'm finding, that same constant is simply multiplied by the limit value. Okay, so if it's a constant multiplier. This one is saying if there's a sum or a difference, that it's just the sum or the difference of the individual pieces of the limits. I can do it piecewise, right? And this one down here is saying, hey, look, if it's a product, also, all I got to do is just multiply the individual limits of the pieces together. So I can break this down into pieces. I can treat the pieces as simplified, parts of it and be able to deal with it, and then just multiply the result, or just add or subtract the result. And those are very nice features. And it's true for quotients as well, as long as the denominator is not 0. If we get a denominator of 0, we got a problem. We've got to do it a different way. And in fact, we talk about what we might do later in this lesson if we have a denominator of 0, how we might deal with that. But otherwise, again, it's the same thing. I have division of limits, so I just divide the limit values. And then this one is kind of I won't say extreme, but a bigger version of this number 3 down here. It's saying that if I have a function raised to a power, then I just take the limit value of the function and raise that to the same power. Okay? So again, nothing that's earth-shattering. It's kind of like everything you wished would be true is happening. You can just plug numbers in. So like on your quiz, when you take a look at your quiz, or not your quiz, but the homework question from section 1.2, where I said we have to look at a graph or a table in order to find out that the limit is 13 over 4 or 3.25. Actually, if you just plugged in the number, you would have also gotten 13 over 4 or 3.25 because it was a line. So as we're taking a look at these and we're trying to find algebraic limits, that's what we're doing. We're trying to evaluate. As long as when I plug numbers in, I get a number out and I don't get a 0 in the denominator, we're good to go and we get the answer. So on the first one, all I'd have to do is plug in the number 1 in place of x squared. And when I simplify that, just one caveat to remind yourself, when there's a negative out here in front, what it means is you do the negative after you do the squaring. Okay? So square things first, and then you're going to make the value negative. So I square the 1, I get 1, and then I make it negative. So I end up getting on this a negative here, 1 squared, which is 1, and then minus 1. So I get 0. Okay? So, yay, I get to plug numbers in. I don't have to look at a table. I don't have to look at a graph. This is way faster. Agreed? Yeah, it's way faster than the last two methods that we described. On the second one, same thing. Yes, I have a denominator, so I need to be careful that I don't put the number in the denominator and I get 0. But sure enough, if I put negative 3 in that x value of that denominator, I don't get 0, right? Negative 3 plus 5 is not 0, so I'm good to go. And I can evaluate the rest of it with the negative 3 in there as well. And if I evaluate all those pieces, plug everything in appropriately, end up with negative 9/2. Okay, so hands up if you like this better than the last two sections. Me too. It's a lot faster. I mean, I'm all about faster as long as I'm not compromising, the process itself. And this is great. It works, and it works correctly all the time. Yes? Oh, I'm sorry. You're right. I was moving too quickly. Oh, no, I had an addition sign wrong. It is 0. This should say plus. Yes, I'm sorry, but thank you, Jared. Yes, I should plus there, so it should be 0, but the arrow was in the middle. Thanks. Okay. The next part kind of talks about what happens with polynomials. So if you'll remember, a polynomial means that you have variables, like a variable x raised to powers. The powers that it's raised to are whole numbers, all right? So no fractions, no decimals, no negatives. It has to be whole numbers, 0, 1, 2, 3, 4, and so on. That's a polynomial. You can have an addition and subtraction of pieces of it together. That's fine as well, but that's what a polynomial is. That anytime you have a polynomial, then you can just evaluate it and plug it in. In fact, that's exactly what we did on number 1. That's a polynomial. Negative x squared plus 1 is a polynomial, and I just plugged the number in. And it works for all polynomials. And because polynomials don't have denominators, again, that makes sense, right? I'm not going to get a 0 in a denominator problem for doing that. But on number 2, when I've got rational functions, I could have a problem. Because on that one, I do have denominators, and the denominator could have the ability to equal 0, and I might, in fact, have a problem. So as long as the denominator is not 0, like it was on number 2 here, I'm good to go. Just plug the number in, move on. Okay, so don't go getting too excited about doing some algebra simplification if you don't need to, right? Just plug the number in and see if it works before you start trying to do other things. But if it doesn't work, what do we do? Well, we'll encounter that in a minute here on example 3. Before we get there, I've got 2 more limit descriptions. This one talks about radicals. So radicals are the equivalent of having fractions or decimals in your exponents on variables, by the way. Not that that's just for free. That's not in my notes or anything. Isn't that exciting? You got something for free today. At any rate, it works the same way, though. If you've got a radical, and as long as the value you're putting into the radical actually doesn't give you like a negative underneath a square root or something like that, you're good to go. You just plug the number in, just like everything else. It talks about this thing about n being odd and n being even. The reason is because we can take square roots of only positives, but we can take cube roots, any odd root of things that are negative as well. So if you're dealing with a cube root of a negative value, again, you've got even greater amount of values that will work because you can take cube roots of negative numbers. For example, just some of you are like, wait a minute, I don't remember that piece. If you had the cube root of negative 8, this is negative 2. And the reason is because negative 2 times itself 3 times is negative 8. And that can work with odd numbers of powers, or odd numbers of bases, but it doesn't work with even numbers of bases. And then the last one talks about composition of functions. So composition means a function inside of a function. For example, let's say you had like the square root of 3x plus 1. The pen's not working very well. 3x plus 1 is a function, right? And it's sort of inside of another function, in this case a radical. So that's what a composition function looks like. It looks like something that's embedded inside of something else. Another one we'll see commonly is something where you have, I'll just use that 3x plus 1 again, and you have it like raised to a power 2 or 3 or 15 or whatever. Then again, it's a function inside of a function. Okay, so this is what this one's talking about. And again, it's telling you the same thing. Just evaluate, and you'll be good to go. All right? So we encountered a couple of examples here, and on these, we actually find out that if, in fact, we try to plug in the value to the denominator, we do get 0. And there's a few things to remember when that happens. When that happens, it doesn't mean the answer is automatically that it doesn't exist. It still might not exist. Like, that's a possible answer, but it doesn't have to be the answer. It could be that you need to do some algebra to simplify what's there. So a couple of reminders about limits when you're doing algebra with them. As long as the algebra is still happening where you're simplifying, you're going to still keep writing limit. Okay, so this piece of it is never going away until you actually plug the number in. It's kind of like when you're dealing with radicals over here. The radical doesn't go away until you actually take the square root, right? You keep putting radical on top of it until you clean things up enough that you can actually do the square root portion of the problem. So the same thing happens here with the limits. That limit notation stays until you're actually plugging the 3 in, okay, or attempting to and finding out you can't. So what we would want to do is we would want to see if we could factor the denominator. And on this one, the video you watched talked about how it would factor. And it factors as x plus 3, x minus 3. It's a difference of squares. The two that look most similar here are the x minus 3 and the 3 minus x. They're almost the same. One of them is just the opposite of the other one. It's like having a negative 3 on top and a positive 3 on bottom. They both have 3, but one's positive and one's negative. And if you have sort of a picture of what that means, is that if I were to multiply this, let me do the 3 minus x. If I were to multiply this by negative 1, what would I get? Well, I'd get negative 3 plus x, and another way of writing that is x minus 3. So they really are the same thing. They're just differ by a factor of negative 1. So when that happens, we can, in fact, simplify and reduce them, cancel them out. But when we do, there's a negative 1 factor that's left over. Once we get it to this point, there's no problem with plugging 3 into the denominator. So this is an example of one where it was 0 in the denominator initially, but once we do the algebra and simplify and clean things up, we can actually plug the number in, and in fact, it has the limit value. So on this one, it would be negative 1/6, right? So what's happening on a graph if you were to look at this? Well, we kind of talked about this early on in section 1.2. What's actually happening on the graph of this one is that I have an equation that has a hole in it. So if you look at it on your calculator, you can't see the hole. It doesn't work like that, right? Because holes are these things that are undefinable width, right? So you don't see that there's a hole there on your calculator. But there is. If you actually go to that value, your calculator will say something like domain error or undefined or something like that if you use the original equation when you're looking for it. Okay, so there's a hole in the graph when that happens. And then on number 4, the same thing happens if I try plugging in 4 to the denominator. It does not work. I get a 0. So again, we look for, can we factor? And if so, will it reduce? And on this one, it does as well. So I'm not going to show you that one because it's the same thing. The factoring is a little bit different, but you've already seen that before. So again, what does it mean? Well, it means there's a hole in the graph at the value of x equal 4. Okay? But you can get infinitely close to the 4, right, from both sides. You just can't actually equal it. This one was an interesting one. If you'll remember from the videos you watched, it talked about the fact that when you end up with this square root business going on, square root of something plus or minus the square root of something else, that you have to rationalize. And it could be rationalizing the denominator or the numerator. This one is an example of rationalizing the numerator. So rationalizing simply means eliminating the radicals. That's what it means. So there's a way of eliminating the radicals, and the way that we do that is we multiply by what's called the conjugate. A conjugate is exactly the same value that you already have, with the opposite sign between the radical pieces. Okay? And if you do it to the numerator, of course, you have to do that to the denominator as well. And the wonderful thing, if you'll remember, that happens when you rationalize, right, when you multiply by the conjugate in particular, is that the radicals on top eliminate, because when I multiply the first terms together, I'm multiplying something by itself. The radical goes away. And when I multiply the last terms together, again, square root of 2 squared is 2, so the radicals go away. And again, the reason that I don't have it to worry about the inside and outside is because this piece and these two pieces multiplied are identical, except one sign's positive and one sign's negative, so they add to 0. Okay? And what that's really doing is it's like the difference of squares that we saw happening over here. Why is x squared minus 9 not have the linear term x in the middle? Well, because it's x plus 3 and x minus 3. It's a difference of squares. So that's kind of where that came from. So when you do this, you do some manipulation, right? It simplifies beautifully on top. The denominator is now messy, and you kind of feel like, okay, well, that was sort of pointless. I just moved the radicals. And you do, except that when you moved the radicals, you actually had a positive in between them instead of the negative you originally had. And with the positive in between them, I can plug the number 0 in. With the negative, I couldn't. And that was the problem. So things simplify, things eliminate very nicely. And again, you don't leave off the limit step. I don't have it on what I just wrote because it's not rewriting what I'm equaling. I'm just multiplying on the top and bottom. But you don't leave off the limit as x approaches 0 until you've actually plugged 0 in. And then a couple other things here at the end were trigonometric functions. And again, it's beautiful. It just says you can plug the number in. As long as it's in the domain, you can plug it in, you can plug it in. Now, sine and cosine, their domain is everything, you'll remember from trig. That's not true for the other 4 functions. So there are things that you can't plug into 3, 4, 5, and 6 here. But those are the ones that you would have to do some sort of a trig manipulation to simplify and reduce things if that happened. All right, last thing, this is what I was remembering. I thought it was in this lesson, that your special trig function limits right here. The limit as x approaches 0 is sine x over x, and then is 1, and then 1 minus cosine x over x as x approaches 0 is 0. I didn't prove it. Your book does talk about why that's the case, but these are facts to remember. And then I had some examples of how to manipulate a little bit, plugging in values, remembering unit circle things. If you don't have a remembrance or it's a little fuzzy on the unit circle, I would encourage you to print one out. You can get a unit circle image online. Just Google it and print it out so that you have it as a reference point, and make sure that you have that down again by the time the first test comes, so that you don't have to be struggling with trig in the middle of a calculus test. Okay? Any questions from my 15-minute conversation about lesson that took, I don't know, 45 minutes or something for you to watch? Okay, so this assignment is due on Friday on WebAssign, and there was no written homework with it, so it's just the WebAssign homework for that. If you have questions, come see me, go to the Success Center, just like they were talking about here at the beginning of class, and you'll be good to go.